For our project, we worked on a car suspension system. Our team members' names are Justin Smith, Sage Bailey, Travis Flanders, and Bizina Huiniashvili. For the project, we considered Honda CR-V as our experiment vehicle. According to online data, the weight of the car is 3,413 pounds. However, converted into kilograms, it's 1,548.1 kilograms. Distribution of a mass is 58% up front, 42% in the back, and left to right is 50-50. Weight of the wheel is approximately 51 pounds. Converted that to kilograms is 23.1 kilograms. System will be analyzed as a single wheel or quarter of a car, and then applied to the rest of the vehicle. Free body diagram is shown in the figure 1. Current suspension system modeled as a spring mass damper system. Wheel and tire modeled as another spring mass damper system in parallel with the suspension system. This system has 3 degrees of freedom: the position of the car, wheel, and the ground. We assumed that stiffness of the wheel is 270 newtons per meter, and the damping coefficient is 300 newton seconds per meter. Experimental acceleration measurements were taken using the ADXL 335 triple axis accelerometer shown in figure 2. The accelerometer was placed on the car, and acceleration data was collected after various forces and initial conditions were placed on the car's bumper and released. The accelerometer measured the reaction of the suspension system.
The design specifications, we assume that the initial displacement would be y equals 0.1 meters, which is approximately the size of a small bump in the road with a sinusoidal input. We designed so that y2 would be less than half of that, and that t would be less than 2 seconds. The car displacement design condition allows for minimum discomfort of the driver and passenger. The settling time allows the vehicle to reach a steady state condition in a relatively short amount of time. The quarter car mass of the front is 448.95 kilograms, and the mass of the rear would be 325.1 kilograms. And our starting point for finding the stiffness values, typically at rest, the spring could be compressed to about 25%. The spring length for the front of the vehicle is 0.393 meters, and the spring length in the rear would be 0.267 meters. The compressed length for the front is 0.09825 meters, and the compressed length for the back would be 0.06675 meters. The force on the front quarters of the car would be equal to 4,404.2 newtons, and the force on the rear quarters would be 3,189.2 newtons. The spring rate in the front is 44.8 kilonewtons per meter, and in the back it's 47.8 kilonewtons per meter. These values were just starting points for our design. And the starting point for finding the damping coefficients, we looked at the typical damping ratio for a passenger car, which was roughly 0.2 to 0.25. The damping ratio is equal to C over 2 times the square root of K times M. So therefore, if we set the damping ratio to 0.225, we could find a theoretical value of the damping coefficient. So the damping coefficient for the front, we found to be 63.8 kilonewton seconds per meter, and the damping ratio for the rear was 56.1 kilonewton seconds per meter. These values were just theoretical, and they're more starting points for our numerical method.
For the quarter car equations, we found that the mass was equal to 387.025 kilograms for the rear. Our spring rate was about 96 kilonewtons per meter. Our C is equal to 3,500 newton seconds per meter. The mass of the wheel is about 23.1 kilograms. The spring rate of the wheel is about 270 newtons per meter, and the damping coefficient of the wheel is roughly 300 newton seconds per meter. Our initial Y value for the input is 0.1 meters. We found YT is equal to Y0 times sine omega t. Y0 is 0.01 meters, and omega is 3.5 radians per second. If you look at the mass of the car compared to the mass of the wheel, the ratio is about 67.02. The ratio of the spring rate of the suspension system to the spring rate of the wheel is about 355.56, and the ratio of the damping coefficient for the suspension compared to that of the wheel is 11.67. For our equations of motion, we first looked at the forces that act on the car. So we have mass times acceleration of the car is equal to the damping coefficient times the displacement of y1, which is the wheel, minus y2, which is the car, plus the spring rate of times the displacement of the car, or displacement of the wheel minus displacement of the car. Converting that and setting it equal to 0, we get mass of the car times the acceleration of the car plus the damping coefficient of the spring, or the suspension system, times the velocity of the car plus the spring rate of the suspension times the displacement of the car minus the damping coefficient of the suspension times the displacement of the wheel minus the spring rate of the suspension minus, or times the displacement of the wheel is equal to 0. So that'll be our equation 1. To find equation 2, we found the forces that act on the wheel. So we found that the mass of the wheel times the acceleration of the wheel is equal to the spring rate of the wheel times the displacement of the ground subtracted by the displacement of the wheel plus the damping coefficient of the wheel times the velocity of the ground subtracted by the velocity of the wheel plus the damping coefficient of the suspension times the velocity of the car subtracted by the velocity of the wheel plus the spring rate of the suspension multiplied by the displacement of the car subtracted by the displacement of the wheel. Converting that to set it equal to the displacement and displacement and velocity of the ground, we find that the mass of the wheel times the acceleration of the wheel plus C plus CW times the acceleration of the wheel plus K plus KW times the displacement of the wheel minus C times the displacement of the car minus K times the displacement of the car is equal to the damping ratio of the tire times the velocity of the ground plus the spring rate of the tire times the displacement of the ground. We use Laplace transform so that S can represent the derivative of the given displacement values. We set equation 1 on the top. So we have MC S squared plus CS plus K, which represents our Y2 values for equation 1. And then on the right, we have minus CS minus K, which represent our Y1 values for equation 1. On the bottom of this matrices, we have equation 2. So for our Y2 values, we have minus CS minus K. And for our Y1 values, we have mass of the wheel S squared plus the quantity C plus CW times S plus the quantity K plus KW. And on the right side, we have set this equal to what the equation 1 and 2 are equal to. So for equation 1, it's 0, which is the top. And equation 2, we have CWS plus K, which represents our initial condition. So after using Cramer's rule to find this equation, we can get YC over Y is equal to the matrix 0, and then minus CS minus K for the top, and for the bottom we have the quantity CWS plus KW, and on the right we have MWS squared plus the quantity C plus CWS plus the quantity K plus KW. To get this, we plug in the column on the right of the equal sign and replace it within the column of the left side of our main matrices. And then the denominator is just our original matrices. So we have MCS squared plus CS plus K on the left, and then minus CS minus K on the right. And our denominator, or our bottom row, is minus CS minus K on the left, and on the right we have MWS squared plus the quantity C plus CWS plus the quantity K plus KW. Once we cross multiply, we find our final transfer function of the displacement of the car over our initial condition Y. So that is equal to the negative of the quantity minus CWS plus K times minus CS minus K. And our denominator is minus the quantity negative CS minus K squared plus the quantity MCS squared plus CS plus K times the quantity MWS squared plus the quantity C plus CWS plus the quantity K plus KW.
Using the transfer function developed, we created a Simulink diagram in MATLAB. From this diagram, we were able to use the SISO tool to test different spring and damping coefficients in order to design the suspension system of the car. This allows us to see how our design system would react in an actual car system. For the front tire of the car, the following step response plot was created. Shown in figure 3 is a step response plot for 1/4 car with the following conditions: a step input of 0.1 meters, the car mass being 448.95 kilograms, and the wheel mass being 23.1 kilograms. The design conditions, which we designed to create the best response, whereas K equals 96,000 newtons per meter, and this with a seat damper of 3,500 newton seconds per meter. The results of these design conditions were a suspension peak amplitude of 0.003 meters, a settling time of 1.77 seconds. These reactions are within the design parameters which we set at the beginning of the experiment. For the rear tires, the following step response plot was created. Shown in figure 4 is the step response for the rear wheels of the vehicle under the following conditions: a step input of 0.1 meters, a car mass of 325.1 kilograms, and a wheel mass of 23.1 kilograms. The conditions that we designed the springs to be the springs was a K of 90,000 newtons per meter and a designed seat damper of 3,500 newton seconds per meter. The results were as follows. There is a peak amplitude of 0.0227 meters and a settling time of 0.838 seconds. These results are also within the design parameters we set forth earlier. It is seen that the optimal spring coefficient for the rear wheels is slightly smaller than the spring coefficient from the front wheels. This is due to the difference in mass between the areas of the car. The way we have designed the system will provide a smooth ride for the driver and avoid any rough terrain.